Before that happens, you have a electric current constantly moving here. Oh, suppose this is a light bulb. If you turn on this one, it's lighting. Right? Unless this is auto power, it's always on. Alright. The thing is, we have a potential difference. V, we call it voltage. And another one, you have a current flow inside. At the beginning, you can use a small battery, for example, just the AAA one, 1.5 volts. Then, how strong the current is inside the circuit. Can you measure that? Yes. People design a small device called ammeter. Oh, double M. The ammeter is designed to measure the electric current. And okay, if you have such a thing, okay, put it in this circuit. And usually we label it as this. A circle inside, you write an A. And people know, okay, that's an ammeter. It's used to measure the current. And the reading is going to be the I, in amps or milliamps or microamps. All right, suppose you measure the current under this condition. It's, for example, 0.2 amps. Okay, then we need to try again. Oh, that's a small battery. It's too weak. Okay, double it. If you have two batteries connected together over here, you will have a higher voltage, right? So how the current is changing. Therefore, you just pick up this reading and record it. Something like, okay? You just keep doing this. All right, so 3 are not enough, double it. Okay, 6.0, which means you have 4 AAA battery over here together. That offers a 6 volts. So how strong the current is here, you can pick up the reading again. It's something like, you can keep doing this a lot of times, right? Therefore, you have a data table. Just like what we did in the lab. You just do a simple experiment. Constantly increase the voltage here to see how the current is changing in the circuit. And suppose that's the data we have. We need to study this to see what we can find. They follow what kind of rules. Therefore, what he did is, okay, simple. You put a voltage over here, you put a current over here. You can draw a curve, right? Okay, the first one, 1.5. That's 1.5. Therefore, double it is going to be 3.0. Double it, 6.0. Something, and 0.2, 0.4, 0.6. All right, let's find all the points you have. The first one is right here, and 0.2, right? That's the first point. And the second one, 0.3, right? Oh no, 3 is over here. It's 0.38. It's close to here, but not equal to 0.4. Somewhere over here. And the third one, 6. And the solution at 0.8 somewhere over here. Okay? And probably you can have more points if you do it continuously. Then if you look at the points. Oh, it looks like a what? Straight line, huh? Okay, can you do a curve fitting? Oh yes, of course. And that's easy. And the computer can do it for you. But at Ohm's time, there's no computer. He has to do it manually like this. Okay, it's a straight line, which means what? Something must be a constant, right? Straight line, at least the slope is a constant, right? So what's the slope on this graph? This is V, this is I. How do you calculate the slope? We just pick up randomly 2 points on the line. See? You have a triangle, this is 90 degrees, right? What's this? This is the change of voltage, right? What's this? The change of current, right? Therefore, basically what you have for the slope here is this. And obviously, if this is a straight line, it equals what? A constant. Therefore, something is interesting over here for this circuit. Oh, this ratio is a constant. What is it? Currently, no idea. We don't know. Just a constant, okay? Suppose this constant is obvious over here. It's basically 1.5 divided by 0.2, something like 7.5, right? All right, let's put this down. Forget about that. We need to make a change here to see what's the meaning of this number, right? Or you are using a light bulb, for example. What's the metal piece inside light bulb?
Filament?
Yeah.
Oh, what is it?
What kind of
element?
metal?
Is it no, it's not mercury.
It's tungsten.
Tungsten, yeah.
Constant, yes. Okay, that's constant, okay. Oh, at least we know this number belongs to tungsten, right? Okay, this belongs to tungsten, okay. Can we change this light bulb? Of course.
Yes.
Let's change it. And we write it down as this sign. Okay, we have another different device, for example, a toaster at home. We connect the toaster over here. And what's the metal inside the toaster? Some kind of metal, but obviously not this one, not tungsten, right? Something else. Suppose it's steel. Okay, iron. Okay, we can do the same thing over here, right? And the battery, we keep those numbers unchanged. We measure the current again. But amazingly, this time the reading all changed. And if you have iron connected over here, this is no longer that. It is 0.17, for example. It's a little bit smaller. Okay, therefore this one, what is it? Okay, something like 3.5. And this one, what's this? Okay, something like this. Can you do another curve there?
Yes.
Oh yes. I'll just try to find the points. And the current is smaller, therefore finally you got a line over here, something like this. Can you calculate this slope? Of course, if you calculate this slope, obviously this slope is larger than this one, right? Therefore, the second slope for iron is going to be something like 8.2 something. Okay? Okay, but that's not convincing. Okay, if you don't trust this, can you change this one to something else?
Yes.
Oh yes, for example, how about a refrigerator? Oh yes. Put a refrigerator here to see how the curve is changing. And of course, it's going to be changed to something like that, for example. And for this line, you have another slope. And that slope belongs to the refrigerator. Oh, finally, Ohm realized, oh, that's the truth. Oh, this ratio is a constant for a certain material. Therefore, it reflects. This is the property of the material. And what's the function of the material for the current? Yes. It basically tells you how strong the resistance is inside the material, right? Therefore, the so-called resistance is basically the property of the material. And what's the relation? That's the relation. Whenever you calculate slope, you have this Therefore, we have to define something new over here. It equals delta V over delta I. And what is it? We call it resistance. And it's a constant for certain material. And this equation becomes the famous Ohm's law. All right, let me erase this one and write it down formally. And this experiment is very, very simple. Anybody can do it, but unfortunately, you guys were born too late. Somebody already discovered. If you were living at his time, maybe it was you. Okay? So Ohm's law. Again, I don't like the way to introduce Ohm's law in the book. And the author tried to derive it. That's not true. This is a pure experimental law, not from the theory. Okay? But if somebody wants to try, it's fine. But basically, it's from experiment. And we remove the delta from the equation. Just potential difference over the current. And R is called the resistance. It equals voltage over current. That's the meaning of this equation.
That's an I, right? Not a 1?
I
Yeah.
is I. Again, so resistance is a new stuff. We want to know the unit of it. And the unit is basically already given. And the numerator is volts. Denominator is amps, right? Okay, therefore the unit is 1 volt per amp. And do you have a special name? Yes. Because Ohm discovered this relation, we just simply use his name as the unit of resistance, but we have a different character. We use this sign for ohms. How to pronounce this one?
Omega.
Omega, yes. An Omega watch. A few $1,000s. I want one, but too expensive. That's the unit of resistance, ohms. And the ohm is a small unit, basically. Any electric device, it has a larger number. For example, the light bulb, at least a few hundred ohms, the resistance. Okay? Okay, that's resistance, but we have another formula for resistance. And all the wires, they have the same shape. What's the shape of the wire if you remove the plastic wrap? Cylinder, right? All the wires, no matter what kind of material, they are made as a cylinder. Okay? We better have a formula to calculate the resistance of a wire. All right, suppose a wire of a lamp of L, for example, and a radius of small r, for example.